in the series. Yeah, so the sixth talk will be given by N Raghavan. So it will be his second talk and his concluding talk. Yeah, so thanks, Raghavan. And yeah, the floor is yours.
Okay, thank you. Thank you once again for the invitation to speak. Let me begin with a shameless plug for some videos of a course on linear algebraic groups that I gave. That's the first thing up there. In case you might find it useful, you might also find it boring because it is full of the under the hood kind of stuff. You might just want to drive the car without bothering to know how the car works. Okay. I myself feel like I know a little bit of what is under the hood, but I can't drive a car. I mean, I know how. I don't know the applications really to complexity, but there are other people to take care of that. Okay, so the topics, the first topic today that I understand I have to cover is what is called categorical quotient, affine place. So, so let G be a reductive affine algebraic group. Okay, so last time, I guess Upendra talked about reductive algebraic groups. Again, this is something, maybe it's not defined very well, not defined at all, not just very well, but we'll not worry about it and just say that GLNC, SLNC, things like this are examples of reductive algebraic groups. Let me say a few more things. Let me also just recall for you affine algebraic group. The way we defined it in my last lecture was that it is a group object, affine algebraic group. This is a group object in the category of affine algebraic sets or affine varieties. So it's basically a variety which is also, there is an underlying group structure on the set of points, on the set of closed points of that variety, and the multiplication and the inverse are morphisms. That's all that means. Okay, reductive. This is, I looked at Upendra's notes and he said it is a structural thing. And yes, indeed. And so let us not worry about it. But one consequence of this, so we are always over C. Reductive implies linearly reductive. Okay, and we can understand this. What this means is that the category of modules is very simple. I'll explain that. If you understand those words, then fine. Otherwise, I'll explain. What this means is that every, let's say, finite dimensional representation, meaning rational representation, I'll just say representation. It is understood that whenever we talk of representations, so representation means what? It's a group homomorphism from G to GLV for some, I have assumed finite dimensional. So it's from G to GLV, where V is some finite dimensional vector space. Now this must be a morphism of affine varieties as well. That is what it means to say that the representation is rational. Sometimes in some books they say even regular. Okay, I don't know if regular is such a nice word to use because the word regular representation has some other meaning in other contexts. But anyway, what it means is that the map from G to GLV is a morphism of varieties in addition to being a group homomorphism. So every finite dimensional representation, not representations, representation is a direct sum of irreducible representation. So recall what an irreducible representation is. An irreducible representation is one that has no non-trivial sub-representations. So given a representation, the whole representation, of course, is a sub-representation. The zero subspace is also a sub-representation. It should not have anything else. Now, just a bit of hair splitting here. The zero representation itself is not considered to be irreducible. Now, the reason for that is similar to the reason that you don't consider one as prime. Because you want to say, see, if the problem with considering one as prime is the following, then you cannot have uniqueness of, you can't, standard fundamental theorem of arithmetic, every positive integer can be written uniquely as a product of primes. That you cannot say, because then I can write 6 as 2 times 3 times 1 times 1 times 1. So 1, you should not assume prime. And for a similar reason, you don't want to assume that 0 is an irreducible representation. Okay? 0 is not considered. So what you can say, given that fact, given that convention, is that the decomposition, okay, I'll come to this later again in the talk. So what you want to say is that the decomposition into irreducible representations is unique in a certain sense, just like similar to the decomposition that in the fundamental theorem of arithmetic. Okay, so we'll come to that slightly later, but this is what it means for a group to be linearly reductive. And this means it's equivalent to another thing, that every sub-representation has a complement. Meaning there is another sub-representation which, when I take the direct sum with, I'll get my representation. So if what this means is, if W is contained in V is invariant, meaning sub-representation, then there exists W prime sub-representation such that, well, let me write G invariant. G invariant such that W direct sum W prime is. This is what linearly reductive means, and reductive implies linearly reductive. Okay. So it is easier to understand this definition and its consequences. Now coming back here, so this is an reductive affine algebraic group, for example, GLNC or SLNC. X is an affine variety on which G acts morphically. This just means you have G cross X to X. This is an action, and this is a morphism of varieties. Then the invariant ring, so let me write it like this, AXG is finitely generated, okay, as a K algebra, as a C algebra. Okay, one comment here, I keep writing K and C. The K is actually C. I could have written C here, but when I feel more comfortable when I write Kx as Kx means the ring of functions of X. And somehow in that context, I prefer to write K rather than C. Okay. Let me Let me move this here. I need more space. Okay. Okay, let's understand, let's more comments here. So this, let's understand what this means. So, so last time, I guess Upendra, in Upendra's lecture, he would have mentioned this, that this, so uh, let's start over again. G acts on X, right? That's what we have. And once a group acts on X, it acts on all objects related to X. So in particular, G acts on the ring of functions of X, the ring of regular functions of X, okay? As an algebra automorphism, by algebra automorphism. Okay? And then I can talk about the ring, the functions that are left invariant under G. So this is by definition all those. This is by definition all those f in kx, all functions such that when I add G on f, I get back f. Okay, and recall that G of f acting on x is f of G inverse of x. That's how the action is defined on kx. The action of G on kx is defined, and this is the ring of invariance. So what we are saying is that that ring of invariance is finitely generated as a C algebra. Okay, as a C algebra, this is finitely. Now this is this of course is the ring of functions of x, and this is a finitely generated C algebra. So such things are called affine algebras, in case this term has not been used before. Okay, so we have here an inclusion of affine algebras. The key point here is this need not be finite. You know, if I take some arbitrary group and arbitrary x here, this need not be finitely generated. So all these assumptions that this is a, this is an affine variety, this is a reductive algebra, reductive, and therefore linearly reductive since I'm over C, assures me that this is a finite algebra. And then I can start. That's where our whole thing starts today. So given that this is a finitely generated algebra, there is a, it is the ring of functions of a variety. Why is that? Well, by now it must be clear from the talk, my previous talk and Krishna's talk, that there is a one-to-one correspondence between affine algebras and affine varieties. So there's a one-to-one correspondence between affine varieties and, I should be more precise here, and reduced affine algebras. And what is that correspondence? Well, given a variety, I can take its ring of functions. Right? So this is a reduced. So if, for example, K is the C is sorry, X is embedded in C and some affine space, then this is just C adjoin n variables for the coordinate functions on Cn modulo the ideal of functions that vanish on X. Okay, look, this is a radical ideal, and therefore this is a reduced algebra. So this is a reduced affine algebra. In the reverse direction, what do I take? In the reverse direction, all I need to take is that uh, in terms of the underlying set, you can take the max spectrum. So the set of maximal ideals, the maximal ideals of AX. This has its Zariski topology, and that will be, so the underlying set of points will correspond to the maximal ideals of this ring, and then this has a Zariski topology on this, and this is this one-to-one correspondence, and it is opposite in the sense if you have a map from X to Y morphism of affine varieties, then the corresponding, there's a reverse map of pullback of functions from, if it's from X to Y, then it will go from KY to KX. Now, with that recall, what we should ask ourselves is the following. Look, this is an affine algebra, and it is contained in this affine algebra, right? And we know what this corresponds to. This corresponds to X. Question is, here is, we have an inclusion of affine algebras, okay, and this corresponds to a variety, and that's what I have asked. What is the description of the variety corresponding to the invariant ring? That is the question we ask. And moreover, since this is an inclusion, this is a map, this is an algebra morphism between affine algebras. So there is a corresponding map from X to this spec or max spec of KXG. Right? What is this? These are the two questions we want to answer. Okay, I hope this is clear, and this is the main thing, and the answer is a very beautiful one, and I'm going to tell you the answer right away. It's like letting the cat out of the bag, but perhaps that's best for, and then we can look at a few examples before we look at some proofs. So this is a good time, I think, to pause and ask if there are any questions.
Yeah, no questions in the chat also. So
okay, proceed. Yeah. So to recap, so G I've assumed is reductive, which means it's linearly reductive, and therefore by Hilbert's theorem, this is a finitely generated algebra. It's an affine algebra, and it's naturally included in the ring of functions on X. And the question, therefore, is what is the variety corresponding to this algebra, this invariant ring, and what is this map? Okay, and what is the answer? Right. The answer is quite simple. It says the following. So let me make an observation here. This, whatever this map is, here is an observation. The corresponding map of varieties is constant on all points. Let's observe that. Why is that? So what I'm saying is, I want to describe this as a variety, at least its max spectrum, and say what this map is. Okay. Now, what I observe is the following. This is an affine algebra, and affine algebra, if you have 2 points, then you can always find a function on it which is 1 here and 0 in the other place. So you cannot have there is the difference between affine varieties and projective varieties. One of the differences is that on affine varieties there are lots of regular functions. So you can separate points. That is, there is a function given 2 distinct points. There is a function which is 1, which takes value 1 on one point and 0 on another. But let's look at this. Now, if I take X here and Y here, sorry, X prime, let's call it X and X prime. So let me Let me now use a different color. Look at this. So x and x prime here. And suppose they are in the same orbit. So suppose gx is equal to. Then look at, I take the functions here are g invariant. So if I take a function here, call it f. Now f of gx, right? This by definition is g inverse of f of x, right? The way g inverse of f is defined. You know, we have defined it here, right? This is my definition here of the action. I'm using that, okay? So, but this is f because f is in here, so it's g invariant, right? So this is f of x, right? So this is equal to f of x. So f of x prime is equal to f of x. So if two things are in this, if x and x prime are in the same orbit of g, then any of these functions here are the same on x and x prime. So if when I map them, if I take the image of x and the image of x prime, it follows that they must be the same. Because if they were not, then there must be some function here which separates those two. Okay? So one obvious thing is that this is constant on orbits. Okay. Now comes the description of what this is. So here is the answer to those questions. And this is the main topic for today's lecture. That it says the following. So max spec of kxg has a very nice description. It is the set of closed g orbits in X. So you can identify it with the set of closed g orbits in X. Okay. Okay. And what is the map? So we denote this X. This is the notation. Okay. If it was just orbit space. Okay, I'll come to this some explanation of why this notation, why this double bar slightly later. Okay, and what is this map from X to this? It is the following: take an element X. What should I map it to here? Look at its orbit, that's Gx, right? And look at its closure, and the claim is this contains a unique closed orbit. And so you map it to that closed orbit. Okay, so that is the content of the main result of today that we are going to talk about. Okay, again, if you have any questions, please ask. Let's look at some examples. Real and C acting on Cn, right? So what are the orbits here, right? So it is transitive on non-zero elements, right? That is, any vector, any non-zero vector can be taken to any other non-zero vector by the action of an invertible matrix. Therefore, there is only one closed orbit, namely the 0 point. Okay, so and if you look at this, so this is my x. So if I take this to be my x, and if I look at kx, the ring of functions, which is the polynomial ring in n variables, and there is an action of GLN C on that. If I look at the invariant ring, Let me, if I look at the invariant ring, it turns out that there are no invariant functions other than constants. Okay, and so there is really a single closed orbit, and that corresponds to the max spec of this. And this has only one max spec, namely the zero idea. Okay, so here, so this is X, this is V. This is the single point. Now, the reason why, okay, maybe this is a good time to explain why this notation. Usually, this stands for the orbits of X, G orbits of X. Here, this is not the map. So what we have is a further quotient, so to speak. What you have is X, the orbits of X, but this is a further quotient, as in this example. You see there are two orbits here. So this thing would contain two elements, namely one for the zero element and one for any non-zero. All the non-zero vectors would be in the other orbit. So there are two elements here. Here there is a single element. There is only one closed orbit. Okay, so this is a further quotient, and perhaps that explains why the double bar. Let's look at more examples. Okay, here is an example to show that really we are using all the hypotheses here. Okay, let's look at, so if I take elements of P1, which are projective coordinates x, y, and C star acting on P1 by P,
Sir?
yeah.
Yeah, in the last example, could you explain the map itself by giving some elements? Say, for example, what happens to E1 100, that point?
Yeah, every point goes to this. There is only one point here. The spec of this,
Yes.
max of, okay. So, so if you want to be more, so the max spec of this is a singleton, namely the zero element. Okay, and any point here, one, as you said, 1, 0, 0, right? That's a valid element of Cn. So as we know from Hilbert, Schultzel, and Sachs, every point of, let's say, the max spectrum of this, of the polynomial ring, there's a one-to-one correspondence of that with Cn, and namely this. And what you do is you take that maximal ideal and contract it here, take its intersection here. Right? And when you take its intersection here, you just get the zero maximal ideal. Is that clear?
Yes, sir. Yeah.
Okay. Yeah. So, this map, you take it as follows. Algebraically, if you want to describe, you take a maximal ideal here, look at its intersection here, contraction, that is this contraction, and here is something interesting. Usually, when you take a contraction of a maximal the contraction of a prime ideal is always prime, but a contraction of a maximal ideal is not in general maximum. However, if you have a map of affine algebras like this, right? One affine algebra over C contained in another affine algebra over C, then you take a maximal ideal here, contract it, you will get a maximal ideal. Okay, that is another version of the Millstone design. I hope that is good enough. I mean, if it is not clear, I can say more.
Thank you, sir. It's clear for me.
Okay, thank you. Okay, questions are welcome. Okay, so suppose I take this action and write Tx y, which is the same thing as x T inverse y. Okay, here there are two orbits. Sorry. Here there are three orbits, and the whole, so the x not equal to 0, so xy, x not equal to 0, y not equal to 0 is one orbit, is an orbit. Okay, it's kind of like C star itself. Okay, if you think of this as C union infinity, and C star is taking away, so C star is C take away 0. So the other thing is 0 and infinity if you wish, or you can call that, what should I call 0? This is 0, 1, and this one is 1, 1, 0. Okay, so these are the three orbits. And if you take this orbit and take its closure, there are these 2 points here. So this illustrates that in general, you could have in the G orbit, I have taken an orbit and looking at its closure, I have 2 points here, which is opposed to the statement here, which says the orbit closure contains a unique closed orbit. Here, as you can see, there are 2 points. These are closed orbits, and both are in the closure of this. Okay, here is another example. C
That's
star
because this is projected, and that the point was that this is
yeah,
E1.
right. This hypothesis of affineness is important. That's yes. Thanks, Kelly. Yes, this is important that this is an affine variety. This G axis, we have assumed X is an affine variety. Here, this hypothesis X is an affine variety. Right. So that hypothesis fails, and the conclusion also fails. Let us look at this once again to illustrate the difference between the orbit space and this categorical quotient. So what is the action? So T times xy is, let's define it to be Tx T inverse y. Okay, if you do this, then so k, so x is c square. So kx will be the polynomial ring in 2 variables. Okay, and if you look at the invariant ring for this action, it will turn out to be generated by xy. Right, that's easy to see because, I mean, there may be some inverses here that I'm fudging, but if I multiply these two, the T and the T inverse cancel. Okay. Okay, so this is, of course, this is like CT, or maybe not T. Let's use a different variable, CU. Okay, so this is like affine one space, and so if you draw a picture of this, you could draw it like this. So each of these, so this is xy is equal to some constant. These are orbits. Then this is y is equal to 0. This is an orbit by itself. X equal to 0 is an orbit by itself. And 0, 0 is an orbit by itself. Okay, so the closed orbits are these xy equals constant and this 0. So that is like, that's like one value, right? It could be 0 or it could be some non-zero value. Let's see. That's a good example to keep in mind. Okay, now we come to perhaps an even more interesting example. So this is something that I had mentioned towards the end of my last talk. So this is GLNC acting by conjugation on MNC. So what we have is K of MNC, right? So this is, you can think of that as K x11, and I have to join n square variables. So let me let me write it as a matrix. Okay, and for this action, what is the invariant ring? So this is X. X is MNC first in this example, and G is GLNT. What is this? Well, it is the coefficient of the characteristic polynomial. How to say this? Coefficients of the characteristic polynomial. Okay, and it's this is a very important example. So let me give you other ways of looking at it. You can think of this also as let me write C here. C adjoined symmetric functions in the eigenvalues. Okay, now this is equal to, so you have the eigenvalues. Okay, let's look at, so if I think of this lambda 1, lambda n as eigenvalues, but see, there is really no, you can't, these n eigenvalues don't come with a number. They come as a set. You can't decide, given a matrix, which is the first eigenvalue or which is the second eigenvalue. So this actually comes with an action of the symmetry. Okay, and so this is like a polynomial ring on which the symmetric group is acting, and this is the ring of symmetric functions. So this symmetric functions in eigenvalues is actually, you can think of it as the ring of symmetric functions in n variables. Okay, that's what this is. So that's what this object is. Okay, and what is this map? This map is, by the way, this thing is also a polynomial ring. This is also a polynomial ring. It's isomorphic to a polynomial. It's a subring of a polynomial ring, which is isomorphic to the, it's a polynomial ring in itself. So the way to see it's a polynomial ring in itself is that these coefficients, these coefficients of the characteristic polynomial, the trace and the second coefficient, etc., up to the determinant, they are algebraically independent. So they form a polynomial ring. And maybe if I say this, it will make more sense. So this is in the elementary symmetric functions. The elementary symmetric functions in these, that's another way of looking at it. So the E1, E2, En, they are algebraically independent, and therefore they are a polynomial ring. And this categorical quotient, therefore, is just the set of eigenvalues. And so what is this map? X going to X mod G is just the set of eigenvalues. So I guess that's a neat description. Okay, so okay, let's go towards some proof. Yes.
Can I ask one quick question? Just
sure.
The eigenvalues are for the X matrix, correct? Which is in the order.
For the X matrix, yeah.
Okay.
So what I mean is, take a point here, which is a matrix. Then I take the eigenvalues of that n by n matrix. I send it to that set. That's what I mean. I hope that is clear.
Yes, thanks.
Yeah. Okay, so towards the proof of this, so let G be reductive and X be an affine variety. Let X, Y, and Z be closed G invariant disjoint subsets of X. So I'm saying Y, so let me repeat this, Y intersect Z is empty. That's my assumption, disjoint. Then there exists a function f on X invariant under G with Fy equal to 0 and Fz equal to 0. Okay. Now, how do I get such a function? Now, let us, so here is a proof. So let me sketch, I mean, the proof is sort of writes itself. Right? Okay, so let's see how that is. Right? So let us forget for the moment that it is G invariant. Right? If Y and Z are closed disjoint subsets of X, let's write J is equal to ideal of Y and K equals ideal of Z. By that I mean all functions on X which when restricted to Y vanish. That's J. So this is all functions on X which when restricted to Z becomes 0. Okay, vanishes. So that this is J, this is K. Now what should be J plus K? Well, because they are disjoint, it follows that this is the whole ring. Okay, very quickly, why is this? Because the reason is simple. Suppose this was not. Suppose, so here is, suppose J plus K were a proper subset of Kx. Then you can take a maximal ideal, right? It would be contained in a maximal ideal. And that would correspond to a point in X. So this I can write as mx for some x in X. Now, every J would vanish on X, right? Because this is the set of functions vanishing on X. And that includes J and that includes K. So, which means X belongs to Y and X belongs to K. Oh, sorry, X belongs to Z. So this would imply X belongs to Y intersects Z, which is a contradiction. Okay, it's just a simple consequence of Nullstein's size. Okay, and then if I forget this part, invariant under G, how would I get such a function? Well, you just take here 1 and write it as it's okay, F plus G. Is G a good letter for a function? Maybe not. K. Let me write K. Sorry, I should have written maybe J here instead of F, but J is a strange letter for a function. Okay, so I take a function. There is a function in J and there is a function in K such that they add up to 1. Okay. Now I claim this will do the job. Right? Now clearly it belongs to J, therefore Fy equals to 0. And if I restrict it to Z, if I evaluate this at Z, K at Z is 0. So Fz is 1 for all Z in Z. Right? So this would be, we would be done. Okay. Now, so how am I going to get this this part? Right? And the answer is simple. What you do is the following. You have the Reynolds operator. Right? If G were a finite group, for example, what you would do is take F and average it. Right? You would just take F plus direct sum, shift it by G and shift it by another G and so on. Right? You would do that. Here, instead of, this is not a finite group, but we have the Reynolds operator. So the Reynolds operator, remember, goes from Kx to Kxg. Okay, and so what I do is I take the Reynolds operator on F, and this does the job. Okay, now there is a little bit of checking here to see that it does the job, and what is involved here is that is the following. So you see here there is this ky, which is an onto map here, and there is a kyg, right? And there is a Reynolds operator here, and there is a map here. So the Reynolds operator for x, and this is the Reynolds operator for y. You have to use the fact that this Reynolds operator is natural. Okay, but it's a very pleasant exercise, and I think this can be safely done. So the idea is the fact that x is affine allows you to separate by means of functions, regular functions, closed sets, and then the Reynolds operator allows you to take, sort of average it over the group and make it an invariant function. That's all there is to it. Now, let us look at, as a corollary of this, let's prove what we claim. Namely, if G is reductive and X is a affine G variety, remember this, that example where it was a projective space, that this hypothesis is important because I cannot drop this. That's what my example above tells us. Every G orbit closure has a unique closed orbit. This is the thing. And the reason again is very simple. Suppose not, right? So suppose I take a G. So I take a G orbit, right? Some G orbit. Let's call it Gx, right? And then this closure had two closed G orbits. Let's say there was one closed orbit and another closed orbit, both contained in Gx, right? Then by this, what we have here, there would be an invariant function on this, which would be 0 on here and 1 here. But an invariant function on this is constant because it's a constant. It's a single orbit. So this cannot be. It's a very simple consequence of this. Okay. Maybe again, this is a good time to stop and ask if there are any questions.
Raghavan, there was one question saying, where did you use the fact that y and z are G invariant in this proof?
Okay. Not until here.
Yeah.
Not until here. See, this up to here, I did not use. Yeah, good question. I did not use G invariance here at all. No G invariance here. This is in fact, so this has nothing to do with G. You have X an affine variety and Y and Z are closed disjoint subsets of X. That's all I'm using here in this part. Right? Then I can find an F such that Fy is 0 and Fz is 1. Here is the argument, along with this notional side, this. Okay. So once I get there, then I average it. That's the, here I use. Here it is important to see, you want to be sure that this RF, when I do it, continues to be 0 on Y, etc. Right? That is, you want it to be, you still have all the good properties. And that is where the G invariance of Y and Z are used. For example, here, when I write this, in order to write this, I need that Y is a G space in its own right. In other words, Y is G invariant. I hope I have answered that question.
Yeah.
Okay, so there are a few things that next, before I have a few more things to say. This sort of finishes the main discussion of today. I have some more examples though, which you might find interesting, and a few more things and some more examples. But before we come to that, let me dispose of some pending material that Upendra suggested that I cover. Okay, so these are a very elementary material from general representation theory, nothing to do with algebraic group representation theory. So, you can just think of this as G is a group and it is acting on a vector linear representations of groups. Okay, suppose I have representations V and W on which G acts, right? So this means the V is a G set. There's an action of G on V. There's an action of V on W, and the if I write V goes to GV is a linear map. So this is from V to V is linear for every G in G. That's what this means. That's what a representation in the abstract is. Right. What is a G linear map? So if I have such a thing, what is a G linear map? Well, it's P is called G linear, or a G map. Let's call it just a G map. If the G action commutes with phi, that is, if I take an X and I act by an element of G here, and then take phi, right? So phi will push it to W. That is the same thing as pushing it via phi to W first, and then acting on G. This makes sense because W is also a G representation. Okay. Actually, you can define this G map even at the level of sets. I have not used anything about these being represented vector spaces and G representations. Right? The notion of a G map makes sense even for G sets. Okay, and I guess this is just for form's sake. I guess all of us know what Schur's lemma is, but it's a very simple thing. It's almost an obvious statement, but it's very important. What it says is the following: suppose you have V and W are irreducible finite dimensional, let's say, G representations, right? And P is a G map between them, G linear map, G linear. It's a linear map, which is G, which is also G. So then P is an isomorphism or phi is zero. Well, the proof is obvious. This being a G map, then you can easily check that the image must be a G invariant space and the kernel must be a G invariant space, right? But the kernel is a G invariant space, so it can only be 0 or V, right? If it is 0, then that means this phi is injective. If it is the whole of V, then it is 0. Okay, similarly, the image is either the whole of W or it is 0. Now, if it is 0, then of course the map is 0. And if it is the whole of W, then it means it's surjective. Okay. Now, another important, let me move this below. Thing here is if I take Hom G, or if I take V is a finite dimensional irreducible G representation, then the G endomorphisms of V is just speed. Okay, again, the proof, if you have not seen, is very pleasant. What you do is you take such a representation, right? Phi from V to V, and it has an eigenvalue, and that along with the fact that it's, it commutes with G, means that if it is not constant, then it will violate this. Okay, I'm not saying this very well, but it's a very pleasant exercise. Okay? I will not spoil it to you.
Maybe you should just explain this notation rather.
Okay, so N G of V. Okay, sure. Yeah. So this means this means all phi from V to V, phi is linear and phi is a G map. Okay, and here is another exercise if you haven't seen this. So end GV. Sorry, I'm messing this up. I should probably move this even. I'll probably mess it because this thing. So just bear with me, please. So this is also equal to end V upper G. Okay. Now what does this mean? Well, G acts on V, and therefore G acts on anything that is associated with V. So G acts on end of V. And this means with our usual convention, all the elements of end V which are left invariant by G. Okay. And that is the same thing as this. So the action of G on end V is, the natural action is suitably defined so that the invariant elements precisely become G linear maps from V to V. Okay, and one more thing is that the multiplicity of any given simple is just another word for irreducible, module in a semi-simple module is uniquely defined. So in other words, if you have a representation and suppose it is semi-simple, which means you can write it as a direct sum of simple representations. Suppose you can, of irreps. Irreps is short for irreducible representations. Direct sum of irreps. Then this decomposition is unique in the following sense. Let me remove this Reynolds operator from here. Okay. In the following sense, that suppose you wrote it as V as a sum of subspace. Let's say 2 copies of some simple module S1. Sorry for the notation, and 3 copies of some simple module, simple representation or irreducible representation. So 2 copies of some irreducible representation S1 and 3 copies of another irreducible representation S2. And then I came along and I wanted to write it. And then if I write it, these, this S1, for example, or this copy, you cannot talk of this copy of S2, but even if I write it, I'll find myself writing 2 copies of S1. And I mean, of course, I can, maybe there will be some permutation, but this is what I meant at the beginning by saying the decomposition into as a direct sum of simple representations is unique in the sense that you must also have S1 and S2, and if I come along and I decompose it separately, I will have also only S1 and S2 and 2 copies of it. If you have 2 copies of S1, I'll also have 2 copies of S1. And if you have 3 copies of S2, I'll also have 3 copies of S2. Moreover, although I cannot say that this copy is equal to this copy, there's one thing I can say, namely, this is the notion of isotypic component. The sum of these two must be equal to the sum of these two. And the sum of these three, see, individually, these could be anything. But the sum of these three is the sum of these three. This is what I guess Upendra talked about, isotypic components. So this is the isotypic component, S2 component. And the isotypic S2 component is uniquely defined. And the isotypic S1 component is uniquely defined. If there are any questions, I'll be happy to answer, but otherwise I'll go on. Okay, let's come to Matsushima's theorem. Okay, let me just give the statement here. I will not try to give a proof, but this gives an example of how to produce reductive groups. Okay, so that is another way of thinking about it. How do I get reductive groups? So here is a statement. So if I take a reductive, let's say GLNC, and if X is an affine variety on which G acts, and the action is transitive. So if the action is transitive, then the stabilizer of any point. So what do I mean by the stabilizer? So in case you have not seen this, so I take a point in X, and the stabilizer of X is defined to be all those elements G in G, such that Gx equal to X. Okay, now this is a closed, from the definitions, it's obvious that it's a closed subgroup of G. Okay, and now what we are saying is this thing is going to be reductive. Okay, that's the statement. So if the action is transitive on an affine variety, then the stabilizer is reductive. Okay, so that's the statement, and I guess it becomes quite important. I mean, so let us look at some example. Okay, so here is an example: Gl2C acting on M2C by conjugation. Now let's look at the orbits. Right? What are the orbits here? We've seen this before, but maybe we'll do it more explicitly here. So there are the closed orbits are those containing diagonal matrices. Okay, and then, so what is left in M2C? So you have non-diagonal matrices, and they look like, by Jordan canonical form, they look like lambda, they look like this. Right? Okay, let us just, you can take lambda to be 0. Let's just concentrate on lambda, then lambda is 0. So for the lambda non-zero case, it works similarly. Right? So let's look at the orbit of this. What is the orbit of this? Well, they are all nilpotent matrices which are non-zero. Okay, and if you work out the stabilizer of this, right? So you can. So what I'm saying is, take the action of Gl2C acts on nilpotent matrices. This action preserves nilpotent matrices. Okay? And how many orbits are there? Well, there are 2 orbits. There is this orbit, and of course, there are 2 orbits. And representatives of those 2 orbits are this one and this one. Okay, and remember there was Krishna in his lecture was trying to give examples of varieties that are not affine, right? And here we have a natural one, because if you look at the stabilizer of this, right? This turns out to be A, B. So stabilizer of, let's call this matrix N, and stabilizer of N is equal to this subgroup A, B in C, A not equal to 0. Okay, that's the stabilizer. And you see that this is not reductive. And therefore, so what you see is, conclusion is this. This is not an affine space. Because if it were, it would contradict this statement. Right? So on this orbit, it is transitive. Then the stabilizer of any point would be reductive if it were an affine variety. But here the stabilizer is not reductive. Therefore, when I take nilpotent matrices minus 0, that orbit is not an affine space. Okay. Okay, now let's come quickly to homogeneous spaces and their structure. So this is something at the level of sets you've seen. So suppose G acts on X and the action is transitive. Then if I take an orbit like this for X and X, then there is a natural, it's identified as a G set. So this is the action of G on X can be restricted to this orbit because it's an orbit. This is isomorphic as a G set to this, where this is the stabilizer of X. Okay, I'm using the notation is, you should pay attention. This is G sub X, which is a stabilizer. This is Gx with X written on the side. This is the orbit of X. Okay, so G acts on this. It's the natural action on the coset space. So this coset space can be identified with the orbit space. Now, the same thing is true at the level of varieties. Okay, so if I have an orbit Gx, then I can identify this with the coset space. Now that brings up the question of how am I going to make this a variety? Now you may wonder, how is this a variety? Well, that follows because, let me just say it. So this is open in its closure. And if Krishna has already defined, I don't know, quasi-projective variety, that makes this a quasi-projective variety. Okay, so the fact that this is open in its closure gives this a variety structure. Now, what we need to do on this side is, the question becomes how to give this a variety structure. And this is one of those things that is at a first pass good to take for granted. So I'll just state it without saying anything more, that if G is an, okay, so if G is an affine algebraic group and H is a closed subgroup, note that here I'm not using anything about reductive or linearly reductive. No, nothing. H is a closed subgroup. Then G mod H is a variety. is a variety, and what is its underlying closed points is the quotient, is the coset space G, this group divided by this by the cosets of this subgroup. It has, so you can look at it as a topological space G mod H, as a set G mod H. They are all consistent. Okay, so you can give this guy a variety structure such that what we understand by that notation in terms of sets, what we understand in terms of that notation in terms of topologies, they are all consistent. And here is the important proposition which will help us do it. Okay. So if G is an affine algebraic group and H is a closed subgroup, then there exists a finite dimensional rational representation V of G and a vector V in V, such that this given subgroup is precisely the stabilizer of the line. So this means GV is in CV. So this is the line, this is the one-dimensional line spanned by V, and this GV belongs to that. If I put this condition GV belongs to that CV, those elements of G that do that are precisely those that belong to H. So given G and given H, I can cook up this V and this little v. Okay. And let me just quickly tell you how to do this. So what you do is you look at the ideal of H inside G, take a set of generators for that, some finite set of generators. This is going to be an Noetherian ring, so you can choose a finite set of generators. And then once you choose a finite set of generators inside the ring of functions, then for the action of G on the ring of functions, there is a finite dimensional subspace, G invariant space, in which all of these belong. And you can take that to begin with, and then you have to do a little bit of jugglery, but all that is very pleasant. It's representation theoretic. You just have to take the exterior product or something like that. But that is sort of obvious because what you will get initially is a subspace that is invariant under H, not a line. And to go to a line, all you need to do is take an appropriate exterior product. Okay, so that's a very, there is nothing new here, really. The new part is what I have described. That is how to start choosing this V. It is a sub-representation of the representation of G on the ring of functions, on the ring of regular functions of G itself. Okay. So let's give some examples here. For example, of this example, G ln C acts on Cn, right? And the lines in Cn are Pn minus 1. So GLN acts on Pn minus 1, right? And the action is transitive. So you can identify Pn minus 1 as GLN minus the stabilizer. Okay, this is an important realization of Pn minus 2 of some point. Okay. Yeah, I'm running out of time. Kelly, is it okay if I take 3 more minutes or so?
Yeah, sure. Yeah, sure.
So if I look at Grassmannians, that's what's a Grassmannian? So you have GLN acting on Cn. Now here we considered lines in Cn, but you can consider, for example, 2-dimensional subspaces in Cn, and that would be an example of a Grassmannian. You can consider 3-dimensional subspaces or 4-dimensional subspaces. Okay. Again, the GLN, so you can, in pretty much the same way that you can make this into a projective variety, this is actually projective space. This has the natural structure of a variety, and GLN action is transitive. So this Grassmannian here is GLN modulo suitable stabilizer is the Grassmannian. Now, becoming even more fancy, there is what are called flag varieties. What you can do is you can fix some, let's say, 2 dimensions. Say, let's say n1, n2. So these are less than n. So you can maybe not, let me call them U and W. So you can fix subspaces U of dimension n1, W of dimension n2 containing here. Look at those pairs, right? Something like this. And then GLN again acts transitively on such kind of things. And you can again get such objects as homogeneous spaces for GLN. In other words, GLN modulo some subgroup will be isomorphic to those objects. These are called flag varieties. Okay. Now, very quickly, let me just give you some more examples from classical invariant theory of this categorical quotient. Okay, so you have GL, let's take GLN or GLV acting on M copies of V, and there's a natural action on V star, and suppose I take Q, right? So this is my X, and this is my G. Okay, and you can ask yourself, what is this KXG? KX, of course, is a polynomial ring in these many variables. Meaning, I mean, there are many variables here. So there is the dimension of V times M plus the dimension of, again, the dimension of V times Q. Okay, so what is this? And an answer is the following. You have these V1, Vm, and F1, Fq are elements here. So you can take these inner products, Vi, F, J, right? And these are functions on X, and these functions are invariant under G. And in fact, this is generated by C adjoint this is I goes between 1 and M, J goes between 1 and Q. Okay, and similarly, you can have the symplectic group acting on V, several copies of V, or the orthogonal group acting on several copies of V, for example. And there are analogous statements. Let me just give you the more very quickly for SLV and then finish. So suppose I take SLV acting on V direct sum M plus V star direct sum Q. Now, of course, anything that is invariant for GLV is also invariant for SLV. So what I get is C. So this is my X, and this is my, this is my G, and this is my X. And I look at what KXG is. And this will be C adjoined all these VIFJ, 1 less than or equal to I less than or equal to M, J less than or equal to 1 less than or equal to Q. But also this time, you will get, you see, VI1, In. So n, let's call this is the dimension of V. And such things where 1 is less than or equal to I1 less than In less than or equal to M, and these FJs.
So the notation, what is this notation?
This is determinant of that matrix. Okay. Now it's obvious that these are invariants. Okay, that's obvious from that. Now, what is not so obvious is that they do generate all the invariants. But that is the examples from these are standard theorems in classical invariant theory. And let me just give you one more interesting statement. What is this as a variety? Right? This is actually as a variety here, this X mod G, what is it? This is the space of all M cross Q matrices. See, this is what I have. These are M, these are Q matrices of rank less than or equal to N, where N is the dimension of V. Okay, so this is like a determinantal variety. It is the space of all M cross Q matrices of rank less than. Okay, I'm over time, well over time. Sorry, I should stop.